Okay, is the screen visible?
Yeah, yeah, visible, sir. Good afternoon, everyone. It is my honor to introduce Dr. Santosh Patil. He is Senior Lead Investigator Sinvent at IDD Syngene International Limited, Bangalore Urban, Karnataka, India. He is the alumnus pride of Bharati Vidyapit College of Pharmacy, Kolhapur. He is um, he has completed his MS from Naipur Mohali, PhD in Organic Chemistry from Macquarie University, Sydney, Australia, and postdoctoral fellowship from University of the Cambridge, UK. He is having 18 years of research experience in industrial medicinal chemistry at Dr. Reddy's Labs Limited, Hyderabad, Syngene Limited, Bangalore, Advinus Therapeutics Limited, Life Sciences Limited, Pune, and IDD Syngene International Limited, Bangalore. He is having drug discovery experience in track record of delivering preclinical candidates and as a program leader for drug discovery cycle, hit lead optimized lead CNN and CSS. Also having diagnostic and technology segment experience in microfluidics technology. He has been the part of international collaborative projects with Takeda, Merck, and others. He is having 12 peer-reviewed articles, 4 patents, and he has been awarded by the International Macquarie University Research Scholarship, CEO Award for Target Evaluation towards Takeda Advinus Collaboration, member of Royal Australian Chemical Society, and he is a member of American Chemical Society. So we welcome our first batch topper, GEM, alumnus Dr. Santosh Patil, who has held the Bharati Vidyapit College of Pharmacy flag high nationally and internationally to this FDB and would like to request him to share his views on structure property relationship analysis. Over to you, sir.
So thank you very much for kind introduction. Am I audible to all?
Yes, sir. Audible.
Yeah. And also thank you very much for accommodating me because I caught in between of my work and I'm sitting literally under tree. Okay. So,
Yes, sir. Thank you so much, sir.
but that doesn't stop me from communicating to you guys because I love you guys. Bharati Vidyapit is at heart of my is at my heart. So with this one, without taking any further time, I will start the session. So this session is not a typical lecture. Here I want you to also participate. Okay. Hello. Am I audible?
Yes, sir. Audible, sir.
Okay. So I'll go to next slide.
Yes.
So basically, there are two pictures in front of your screen. I want to know what is A and what is B. Yeah. Just put your comments into chat box, or you can say there's nothing right or wrong.
It's sugar and salt.
Sugar and salt. Okay. Next one. Say your name and say that. Okay. Guys, lot of quick. I want answers.
Participants, you can participate in the question answer session by resource person.
So I'm Sampath. It is the B1 is salt.
Okay. Yeah.
And A1 is crystals.
Okay. Okay. So so that's great. So actually both are salts. So any more answers?
Hello.
Sir,
Yeah.
B is amorphous in nature, while A is crystalline in nature.
Okay. Now, what is the chemical composition? Can you guess? Sugar and salt, like that.
Okay.
Hello.
Yes, I can hear.
A contains sucrose.
Okay.
Sir,
Can I speak?
Yes, please.
Sugar C6H12O6,
Okay.
salt NaCl.
Okay. Okay. Thank you, guys. Can you now all mute, please?
Okay, sir. Thank you.
Both are white.
Okay, great. I think I got enough responses. Thank you very much. It's afternoon session. You are hungry for lunch. I understand that. So basically, this is my topic. So I go back. It's structure functional analysis in drug discovery. Now you mentioned that sugar and salt, and someone mentioned that. So it's a sodium chloride, which is sugar, which is salt, and then sugar, which is of course sugar in it. So what it is really, one is sodium chloride, okay, and other is sodium cyanide. Can you see my screen? Hello.
Yes, sir. Visible. Screen is
Yeah.
visible.
Yeah. So
Yes, yes,
basically,
yes. Visible,
yeah.
visible.
Yeah. So what it means is that A is, let's say, I also forgot now really. So I think A is sodium chloride and B is A is sodium cyanide and B is sodium chloride. So with this one, what it means is the structure are and function are very important. Both are sodium salts. One is sodium cyano minus and one is chloro minus, and they make hell lot of difference in our body. Even chlorine per se gas is dangerous, but when it combines with sodium chloride, it is salt which we take. It is there in our physiology. You see the cartoon with the the man, where it is everywhere in our body. It helps in conductance of your nerve cells. It helps in basically maintaining the physiological role of our cells. It is in stomach, so it helps maintain the digestive role. So it's everywhere. So that happens because of the sodium chloride nature. And the sodium cyanide, basically it's similar. It's cyano minus. It is again sodium salt, but then you know that it can cause a death in minutes. And beyond that, sodium chloride also is implicated in the explosion which happened in China, where sodium chloride reacted with the hydrogen peroxide gas, and that led to explosion. So you can see the charred cars there. Also, sodium chloride is involved in the basically jewelry making. So sodium chloride reacts with the gold, and gold is isolated. That's what where the gold isolated from the debris. So having said that, so now you know the importance of the sodium cyanide, sodium chloride, and so what I want to say is that structure is very important, and we should link to the function. So that's all about what we do in the pharmacy. So then you have to go deep. You have to look at the structure of sodium. So basically, it has 11 uh, the protons, and then there are 11 electrons, which is 2 to 8 is to 1 ratio. The outer electron is basically can be donated to the chloro minus. You have sodium chloride. So if you look at sodium cyanide, it is also similar structure. 1 electron is donated to the cyano, it becomes cyano minus. And of course, the sodium cyanide reacts with our blood. It reacts with hemoglobin, as you know, and it causes basically oxygen. It limits oxygen capacity, and it leads to death. So what I want to say is really, as a pharma person, you need to really look into the sodium, into the detail of the structure and link into the function. This is the simplest example I took, so that you can understand the importance. It is very one of the simplest example. So now moving on to that, you may be thinking, okay, structures are important, functions are important, but why I should know it? Because I'm a pharma person, why I should know it? So basically, and how is it important for exploring PK with AI and quantum computing? Why I'm being told structure functional thing in this seminar? So can you recognize this picture, guys? I don't know. Some of you may be there in this picture. It's a formulation lab. I remember my days. Can you hear me? Hello?
Yes, sir. Yes, sir. We can hear you.
Okay. So basically, because it's important to know the structure function, because what's happening with drug discovery right now is that despite of tremendous technology advances, we have issues with the drug discovery. Last 3 decades, has not changed the drug discovery cycle. But a drug makes 3.2 billion, for making one drug. And what is happening is 90% time we fail in drug discovery. And that failure is from the target discovery, lead optimization, preclinical. It's all the way phase 1, phase 2, phase 3, and registration. So we fail all the way in the drug discovery, and that cost for launching drug cost around 2.6 billion. So because of that, we should really know the structure and function. If you know that, then we can do our business better. So basically, pharma companies that have been trying, different ways. They are compelling targets like protein-protein interaction, transcription factor, which are difficult. And current way we operate is the DMAT cycle. So people tried high throughput screening where the space is 10⁶, and then DNA and library where you can go to 10⁻10, and virtual screening can go to 10⁻13, and actual chemical space is 10⁻63, which is much greater than the stars, or stars in the universe. So basically, we are improving upon our capabilities in technology, but having done that, we are not at there. So we only the virtual screening, and now artificial intelligence AI came into the picture. So what we want to do is we want to really think smart way. Okay. And then we have fragment-based drug discovery also came into the picture. So we need to really look beyond the conventional technologies or new technology. Even I can say you need to look beyond the AI and basically computational techniques to be successful. So basically, a drug discovery cycle is a long journey. Starts from the phenotypic drugs discovery, from asset development, screening, STS, lead, target deconvolution, where we need to understand where the target really is hitting. Once we know the target, then it starts the target validation, asset development, screening, STS leads. From STS leads, it takes another year or so for lead optimization, admit cycle, and development can take another 6 years, and the registration take another 2 years. So it's all the way 10 years to 20 years for a molecule to become a drug. So in this process, we have to really be smart, and we have to really think deep down into the science. So that's going to basically help us to get to the drug discovery. Okay, guys, you may say now, can you see the screen? Okay, we understood the structure, function are important for drug discovery. Then why pharma? Then how? And we pharma arrive at structure function. How we can understand the structure function relationship in the drug discovery? How we can analyze? How we can correlate structure to function. One example I gave, very simple: sodium chloride, sodium cyanide. One is life, one is death. It just cyano minus, and which is chloro minus. Chloro minus basically regulates all our nerve actions, action potentials, everything. Cyano minus complex with hemoglobin, and and then you are basically you die actually. And also it leads to explosion when it reacts to hydrogen peroxide by carboxylic acid, which is CO2 gas, and that's what happened in China, where a lot of car burn. You saw the picture. And also cyano is reacts with gold to purify the gold. Can you see the picture here, guys?
Yes, sir. Yes, we can see.
Any of you are there in this picture?
Yes, one of our faculty member who is
Yes, yes.
organizing committee.
I'm there.
Yes, he is speaking.
Okay, great. So basically, what really needs to talk here is basically structure function. So that's very important. So can you
आपल्याकडं M-Pharm कोणाचे या delete?
Participants, please put your mic on mute.
Documents म्हणे.
A request from participants, please put your mic on mute.
okay, guys, I will immediately ask you to unmute. Don't worry, in a minute. I have next question. So now we know that structure functions are important. And then question is how pharmacy graduates can link the structure and function, how we can learn. So best way is to learn is analysis. You analyze the things around you. You analyze the things in the nature. You analyze the things around you in the structure, and then you try to correlate to function. So basically, it's all about analysis and then imagination. So I want to ask you one imagination. You take a weighing balance. आपली तराजू जी म्हणतो तराजू घ्यायची. You put all the which is size of Earth. Okay. You put all the living beings, plants and animals in one balance. एका साईडला सगळे प्राणी आणि वनस्पती टाकायचे. For example, from bacteria to blue whale, and from the grass to the banyan tree. You put all of them in one balance, and you put another pan all human beings. Okay, सगळे जिवंत असलेले सगळे माणूस आपण एका तराजूत बसायचे. Tell me how much percentage are we as human beings on Earth? Now you can unmute and you can say the number. How much percentage are human beings on Earth compared to all other living beings?
75%, sir.
Okay, what is your name, please?
Rahul Lohare.
Lahore, thank you very much. Now I want to know from every one of you. I think everyone you should tell one number, please. There's nothing right or wrong. Just say the number. Hello.
Hello.
Yeah.
Sir. Sir, you want to know percentage?
Percentage of human beings on Earth compared to all other living beings. This is
70%, sir. 70.
70%. Okay, next.
10%, sir.
It is less than 1%, sir, because the biological. My name is Manikiran, and what I'm going to tell is like the percentage of humans is pretty less than. I mean to say less than 1% compared to the Earth and all the living beings that what you have told.
No. I'm not saying compared to Earth. I'm saying that on Earth you put all human beings in one balance and all living beings in another balance. So we're not comparing to Earth. We're comparing humans versus animals and plants.
So humans weigh pretty much less than the Earth.
Okay, all other living beings, not Earth. Okay.
All the living beings, because you have kept the photograph, no? So by seeing that, I'm explaining that.
No. Yeah, correct. That is big balance. I want to say big balance. Okay.
Yeah. Okay.
Okay. Thank you, Nikandan. Really good. So we have answer one is 75%, other is 1%. That is quite a diversity. Wow. Really, I'm really happy. Okay. Anyone else?
I guess it will be Kiran Patil here from the same college, Bharati Vidyapit.
Yeah.
It may be 0.1 or less than that even if you compare animals and plants, specifically plants, if at all plants will be there.
Oh, great. 0.1. Wow. Okay. Okay. So guys, other one who don't speak, just keep one number in your mind. Okay. You don't have to say. Okay. So with this one, if you can all mute, I'll go to the next slide. Am I audible to you?
Yes, sir, audible.
Okay. So thank you very much. We are basically on Earth 0.01%.
Yeah, right. It's the human life is 0.01% as compared to other lives.
Correct. And then 99.99% are basically in nature, they survive, they remain healthy. Okay. So to connect structure to function, we really have to look at the nature, how nature keeps plants, animals, everyone, healthy. Okay. So this is basically plants are 82%, bacteria 13%, 5% of everything else, including humans. And in human body itself, we are 90% by number, we are bacteria. I repeat again, human body itself by number is 90% bacteria. Only 10% are we ourselves, our body. Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay. So what it means is that we are not we. So there should not be any ego. If you are ego, and you should take it away, because you are not you. You are 90% bacteria by number. So what it means is that we really have to look into and of course with 0.01% we occupy 86% of land. 86% of land we occupy. Okay. So with this one, we really have to look at the structure function of what's happening in nature. How the this other species is happy. How they survive. They don't have doctor. They don't have hospitals. They don't have medicines. They don't have pharmaceutical companies. These plants and animals don't study pharmacy course. Okay, but they are happy. They're healthy. So way it happens, they have also problems. They are stress, their nutrients, pH change, temperature, iron availability, correlation, oxygen issue, water, light. So they fight among themselves as well by chemical molecules. Penicillin, for example, kills bacteria. So they have a lot of these chemicals. I'm expanding the screen. So they have this natural products. So we need to really look at this each and every natural product and apply this structure to the functional analysis. You can use AI, you can use machine learning, or you can just think yourself. But you need to get to that level, and you have to correlate sodium chloride, sodium cyanide, one to life and one to death. So that way you have to correlate these acids, this natural products, and say how I can make a better medicine out of it. Okay, any questions, guys, here? So with this one, so with this one, I'm just going to the next slide. What's happening is, the bacteria are getting resistance, and research is declining. So we need really antibiotics, new medicines in anti-infective area. So we need a lot of, we are looking at the pharmacy guys. This is something interesting. This slide I put in 2014. They say that without urgent coordination in the post-antibiotic area, the simple infections like minor infection like flu can kill you, and it is happening right now in the COVID situation. The simple virus is basically killing people, and it's completely shut down whole world. So what it really means is that we need to really be very smart to understand nature. We need to really look at this 99.99%. We really look at this 99.99%. How rest 99.99% survive, and we really have to rethink our strategy, our educational systems, our way of thinking. Everything we need to reset now, and that's the pandemic has told us. We need to really think deep down, really look into nature, understand it, analyze it. So with this one, I'm just going quickly to the era. So he started with the dark ages before 1940, called Semeglis. He was a physician. So people used to die after surgery, special doctors, and they found that it is due to infection. This is before antibiotic discovered. Antibiotic discovered in it discovered in the 1940s and 50s. So before that. So then you have the antibiotic resistance issue coming along, and we went to the genomics, STS, now AI, and then again we are going back to the hand washing. When I'm talking to you, if I came to office, I'm with mask, I touch something, I again wash my hands. So again, we are going back to the basically now below 1930s. So we are same where we left. So what it really means is that we need to look at the nature, learn from it, do differently what we are doing. So that's the important message I want to give to you guys. So I'll just skip this. You can have, the slides are with you guys. You can later look into that. This I looked into very detail, how natural selection works, how dynamic works, and I plotted a graph. What is the exact mechanism of penicillin resistance? What is really happening at the molecular level? You can see that penicillin bond is getting cleaved by bacteria, and it becomes penicillin is become not effective. So it is simple. The serine hydroxy group attacks on the carbonyl carbon of the amide bond, and it opens up that way. So what it is really is that we need to really understand the structure to the detail and correlate to the function, and that's what you get the resistance. This is another example how you can correlate structure to the function. So basically what we do in drug discovery, we design molecules, we synthesize them, we assay them, again we do a structure activity relationship. But you focus here, you need to really understand the structure very well, understand the function of it, understand the physiology of our body, and smartly design the molecules. You can take help of AI, or you can be, you can use empirical design, doesn't matter, but it has to be very smart. And what nature does, what it does is, it has a lot of diversity. So it just does the translation, which is DNA to protein, protein to this, DNA to RNA, RNA to protein, protein to the, you can get natural products like alkaloids, the pharmacognosy. You get a lot of other natural products. And then out of that, it selects. It's natural selection. And then it amplifies. It does same thing what we do, but it does very, very smartly. So that's the way we need to really understand at the nature. So what I did when I was at Cambridge, I looked into the basically now here for you, this is the way we compare between the what we do as chemist or pharmacist and what nature does. We have 10 to 12 copies of molecule. Nature has just 1,000 molecules, less than 1,000. We basically do separate assays. Nature does in one pot. Okay, so our sample has 10 to 6. Nature sample has 10 to 15. Okay, and what we do, we can synthesize whatever we have. But nature has nucleic acids and proteins, has the workhorse for synthesis. Nature does all reactions in water. We do basically, we need organic solvents for the reaction. Okay, so really, this is nature laboratory is this. It is your kitchen sink pipe. It is your heart with cystic fibrosis. This is nature laboratory. What is our laboratory? Our laboratory is this 96 well plate. Here we do assay. So what I'm saying is I'm constantly comparing myself, ourselves with the nature and try to see what we can learn. So with this one, what I did at Cambridge is something called directed evolution. 2 years before, the Nobel Prize in chemistry went for directed evolution. What it does, it takes DNA, it randomly mutates, and then it amplifies the proteins, and and then it makes a lot of copies, and you do assay. So this is the directed evolution field which got Nobel Prize, and I worked when I was at Cambridge into the directed evolution. So I'll just skip this. So basically, what we did is we did microdroplet technology, where we have a gene, then RNA, then enzyme, everything in encapsulated, and so we don't miss the information what gene has led to what enzyme. So everything is trapped. So that technology we developed when I was at Cambridge. It is basically using the microdroplet technology. You can see here. So it's different ways to make a different droplets, and then you can analyze. So I'm using the word analysis again. So we need to very careful with analysis and then understand that. So basically, what with this one, this is published in Nature Chemistry. This is a paper. You can see 2014 Nature Chemistry, where I was here. I was with the other guys. We had engineer, we had a biochemist, we have pharmacists like me, and organic chemist. So everyone chipped in, and we did a technology which is now led to a company in Cambridge. Okay, so here we evolved the enzyme. So you can have a look at this paper. I can do one-to-one discussion with you guys. What it is really. So what we did, this is the way we developed this technology. But at the heart of it, it is basically a simple chemistry. So you need to really understand that cations, calcium, glucuronic acid, muramic acid reacts with calcium, form the gel, and then we use this agar gel alginates and to make these droplets. So basically, what I want to say is, when you think of very hi-fi technologies, but at the end of the bottom, it is basically simple science. So you need to really look into the science. So this is one of my favorite slide. This is the technology which is there in, let's say, 1998. People talk about this hi-fi technology called directed evolution, but the basis of it is this paper. It is basically a polyanion layer. Then you have polycation layer, and then you form the bilayer. So this paper basically is in 90. I think this is in 1900 or 1800. So it's very old paper, but I always look at this original research where they talk about sulfonic acid, the sodium salt of sulfonic acid and ammonium chloride, and this is the basis of technology. So you need to really understand deep down for anything anything you want to build upon very complex. So this is the way. I'm just skipping this, and we evolved an enzyme called phosphoesterase, and nature basically takes billions of years to evolve this phosphoesterase enzyme. We did in lab very quickly. Let's say in 4 months, we can get a better enzyme, and it is helping basically to cleave the toxic pesticides and nerve gas. We can cleave it and very efficiently. So you can see the pesticides and nerve gas. We can cleave with this enzyme that we evolved in the laboratory. Again, learning from nature. So this is the facts. I will not go in detail. So conclusion is, drug discovery has been always inspired by nature, and you have to find the new perspective. You have to urgently look into the success of drug discovery. We have to look very carefully at the nature, assay versus selection, and learning from nature can be directed by Professor Chris Abel. And I'm very sad, and this lecture I can give in the memory of Professor Abel, who expired 5 days before. He was excellent scientist. I'll come. I'm waiting here. So he's excellent scientist, and then we completed 800 years when I was there at Cambridge. So here basically this picture is blurred, but Chris is there, my wife is there in sari, you can see, and this is all our group. So with this one, if you guys, I want to unmute you now, please. Can you hear me?
Yes, sir.
Hello? Okay.
Yes, sir. Yes. Audible.
Yeah. So if you forget what the picture, I'm okay with that. Only you remember this tree. So guys, what you see here? Can you tell me what you see here, guys?
It's a huge
branches, sir. We could see many branches.
Branches, okay. Leaves, tree, grass,
greenery,
perfect.
Nature.
Yeah. So guys, can you see the roots?
No, sir.
No, sir. Perfect.
Yes,
I have seen, sir.
Yes.
Yes, sir. Roots could be seen.
Yeah. So I choose this tree, especially it's a banyan tree. Here you can see roots, but not all the other trees you can see roots.
Yes.
Okay.
Yes,
so
sir.
why is that? Why is that? Because what I want to say is your roots should be very strong.
Strength.
Okay.
Yeah.
So what I want to say is we are talking about artificial intelligence, molecular dynamics, machine learning, but you should also learn about fundamental science, fundamental mathematics, fundamental statistics, fundamental chemistry. You have to look at the nature. So basically, that are the roots on which everything is built upon. Okay. So with this one, I thank you for your attention. So yeah, I'm done actually.
Yeah, thank you so much, sir. Participants, the session is open for the question and answer. So if you have any queries, if you want to ask, you can raise your questions. Yeah. There is a question from Dr. S.S. Mani. So you can ask a question.
This is Manikiran speaking from Vignan Pharmacy College, sir.
Yeah.
Thank you for your information, and also you are suggesting like we have to be very strong at our fundamentals. Sir, as you have mentioned from your presentation that except humans, the animals were able to manage themselves, and you have also advised us to see in the nature. So what exactly that we have to focus on so that we can make our lives better?
So, that's very good question. Actually, the problem is in that. Problem is we always think what else we can do to make it this place is better. But problem is that what else we should not do to make it this better. You got my point. So we need to really look into what we should not do to preserve this earth.
Okay. You say like we have to protect the earth and we have to get blend with the nature. That's what you are saying, sir?
Correct. That also, and also whatever we do, whatever we discover, whatever we apply, that has to be with harmony with nature. It's all about life balance. We have to maintain the balance and try to see that we should not disturb the balance. As soon as you disturb the balance, you get the problems like COVID. Bats used to live in the forest. They were not coming very close to human beings. We basically now occupy 83% of land, and we are basically 0.01%. We come in contact with these animals, and then because of the air travel and everything, we spread this deadly virus across the world. So basically, what it does is that we have to really very smart. We have to see what we can do as a scientist, to preserve the earth, to discover something which is basically eco-friendly. To think about how we can discuss some. For example, for antibiotics, you kill or stop the bacterial growth. But can you do one thing? Can you keep them just quiet? Because they form something called quorum sensing. They come together, they form biofilm, they attack you. So can you do something just to keep quiet? Don't kill them or stop their growth.
Okay.
That we have to think about that line. Can we as a scientist educate people? It's about living. As a pharmacist, it's just not after disease. You should not talk to people. We should talk to people how we can prevent the disease. How can we can live healthy? So that's something we have to completely undo what we are doing right now. I am as a part of this. It's very difficult, I know, but at least this thought has to be going down. So that's what I can say.
So from your answer, what I have understood is, so far the medical research has been focusing on the result, but we haven't focused on the cause. So from your talk, I have understood like we have to focus on the cause. It's not the disease that we got to treat. We have to treat the cause which caused the disease. That's what you're saying, sir?
Correct. And it should be in balance.
Thank you very much for your great presentation, sir. Honor to meet you. Thanks for BB Corp also.
Thank you so much, sir.
Thank you, Neela madam.
Yeah, thanks, sir. If any other participants, you have any query, you can ask. Okay, so thank you, Santosh, sir.
Okay. So,
Amelia, sincere thanks to you, sir, for the sea of the wisdom and the knowledge you shared with us during your amazing lecture. It was an absolutely brilliant lecture and definitely a real eye-opener. Thank you for an outstanding lecture. Thank you, sir.
Thank you.
Thank you so much, sir.
Okay, thank you very much. Thank you, everyone. So I look forward to meet you in person.
Definitely, sir.
These slides I prepared in morning 4:30. I started preparing them. So my apology if they're not perfect, but I think still. Then what happened? I completely could not save it. So again, I had to redo everything. So that's what my apology. The slides are not that good, but you can circulate the slides to everyone.
Yeah, sure, sir. No issues.
Okay. Thank you.
Yeah, thank you so much. Okay, so participants, we end with the session 3 for day 2. Tomorrow we'll begin again at 10 o'clock.